I'm glad to introduce Gon here, who's going to talk about scaling inference for generative AI. Welcome, Gon.
Okay. 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 Welcome to the talk. I'm Gon, founder and CEO of FriendliAI. Today, I'm going to talk about scaling Gen AI inference, focusing on key challenges and techniques. Just a few years ago, generative AI was mainly a research curiosity. Today, it's everywhere, from productivity tools to copilots, from creative applications to enterprise workflows. The rapid rise of powerful open source models also contributed to this transformation, making advanced AI more accessible than ever. But behind every magical product lies a massive computational challenge: inference at scale. Inference is the process of getting an output from a model, which is how your customers interact with your AI product. It's directly correlated to business outcomes at scale. As our AI product scales, inference dominates the economics and user experience. Every single token generated requires GPU cycles. At scale, this adds up to billions of GPU seconds per day. In real-world deployments, inference often accounts for 80–90% of an AI model's total lifetime cost. So improving inference is hugely impactful. So companies today face 4 or 5 critical inference constraints: latency, throughput, cost, and reliability. And also time to market. If inference is too slow, users churn. If it's too expensive, business models collapse. If it's unreliable, mission-critical applications won't adapt. Time to market is very important. You don't want to wait for months to get deployed to be scalable. That's why scaling inference is the essential enabler for Gen AI to deliver real impact. So the big question is this: how do we design inference systems that are fast, cost-efficient, and robust, while serving many, many users across diverse workloads? That's what I will dive into today. So let's start with some background. So let's first explore the inference workload like GPT, how inference unfolds in autoregressive AI models. In the first step of the inference, the entire input sequence is processed. This is known as the prefill stage. In each subsequent step, the model runtime reuses the cached key and value pairs from all previous tokens and computes them only for the newly generated token. So this process, called the decode stage, uses a key value cache, in short KB cache, which just stores information on all previous tokens to avoid redundant computation. And this workload runs on GPUs. GPUs are designed for massively parallel processing, making them well-suited for the large-scale computation required by modern AI models. From a systems perspective, GPU software optimization is all about identifying and addressing bottlenecks within the limits of compute, memory, and bandwidth. Most important dimensions to consider are flops for compute power, bandwidth across storage layers, such as transfers to and from GPU RAM, and the size of GPU RAM, which directly impacts how much data and how many requests can be handled in parallel. And lastly, GPUs actually fail more often than you think. So what are the goals we are optimizing for to scale? So we're going to talk about latency, we're going to talk about throughput, reliability, and time to market. Here are some metrics we can use to track how well we are doing. On the performance side, we care about 2 key things: low latency and high throughput. For latency specifically, there are 2 important metrics to track. Time to first token captures how quickly the model starts responding. Time per output token, TPOT, captures how fast it generates each additional token. For throughput, tokens per second or requests per second. And we would like to improve performance while having minimal impact on model quality, and that's given. Because when we apply optimization, we need to ensure that the model still produces high quality outputs. And when we talk about reliability, we care about high uptime, measured in how many lines we can guarantee. And lastly, faster time to market, deploy and scale within minutes, ideally. So now I'm going to switch gears and start with techniques to optimize throughput and latency. To achieve the goals, we apply a range of optimization techniques. There are a lot. So key optimization techniques include batching, quantization, GPU kernel optimization, caching, parallelism, scheduling, speculative decoding, and disaggregated serving. Each technique targets different bottlenecks. Some focus on latency, others on throughput, and some improve both. With friendly inference, you skip the complexity and focus on results. Given the time, I'll walk through some techniques at a high level to highlight the key ideas. First, throughput. The most important optimization for throughput is batching. GPUs have many computing cores, but to make full use of them, we need to give the GPU enough work. In inference, GPU operations involve two types of data: model weights shared across all requests, and activations unique to each request. Batching processes multiple requests together, which reduces data movement and increases arithmetic intensity. This helps shift workloads from memory-bound to compute-bound, but it comes at the cost of higher GPU RAM usage, especially for storing the key value cache. In practice, inference traffic is very dynamic and uneven. Requests come in at irregular times, and they don't all take the same amount of time to finish. That's why traditional batching isn't enough. The industry standard for handling this is continuous batching, also known as iteration batching, a technique we proposed. With continuous batching, you can dynamically add new requests to the batch or remove completed ones from the batch at a fine-grained level, keeping the batch efficiently backed. This allows the system to maintain high GPU utilization even when traffic is dynamic and uneven. We currently use an even more optimized version. So if you're interested, you can check out our Orca paper. Now let's take a look at optimizations that affect both throughput and latency. First, let's start with quantization. This is a bit dense slide. Quantization reduces the number of bits used in data and computation, improving bandwidth efficiency and flops, but it can affect model quality. There is a range of methods depending on which parts of the data and computation are quantized and what formats are used. Quantization helps latency for low batch scenarios and throughput for high batch scenarios. For Hopper, we use FP8. For Blackwell, we use FP4. I would like to highlight that just because two companies say we use 14.8 doesn't mean they are using the same quantization method. Different teams implement it differently. We have our own quantization method, friendly quantization, that preserves model quality while speeding up execution. Next, GPU kernel optimization. GPU pipelines are managed primarily at the software level. How efficiently we schedule and coordinate operations has a major impact on performance. Without effective pipelining, only a small fraction of the GPU's compute capacity is actually utilized. So to fully leverage GPU hardware, we need to overlap execution across different functional units such as tensor cores, CUDA cores, and data transport. We also have to be careful about how we handle numerical precision in handling dynamic tensor shapes. Flash attention is a great example, which carefully restructures attention computation to maximize memory locality and overlap operations, improving both speed and efficiency. And we have our own friendly kernel library, which we have built our own optimized kernels for various dynamic tensor shapes. Now, caching. caching is essential. For transformer models, we use key value cache. Key value cache stores intermediate computations of keys and values across iterations for a single request, and also cross requests to skip prefills when there is a cache hit. There is a trade-off between batching and caching. Increasing the batch size improves throughput, but it also reduces available memory for future cache reuse, thus affecting cache hit rate. And friendly caching covers more. It supports multimodal data, not just text. It integrates with CPU RAM and NVMe SSD for larger cache capacity. It optimizes with cache error routing when you have multiple model instances. So next item is parallelism. Parallelism across GPUs improves both latency and throughput. Tensor parallelism is the default. But for MOE models, expert parallelism can be also used, partitioning experts across GPUs. In production, there are different configuration choices depending on your MOE model setup and your workloads. And you can combine tensor parallelism and expert parallelism. We often found that in some cases, just using tensor parallelism works well. In other cases, combining expert parallelism with tensor parallelism is better than just using tensor parallelism. Now, latency. Speculative decoding is one of the techniques that can improve TPOT. It generates multiple tokens per forward pass to improve TPOT, helping shift the workload from memory bound to compute bound. And note that it is effective in low batch scenarios. If you have a large batch, using spec decoding actually hurts performance. In the speculative decoding, a small draft model is used to propose tokens. Then the original model validates the draft tokens. The key trade-off here is between how many of those draft tokens get accepted and how much compute it takes to generate them. And we have developed a lightweight spec decoding method with high draft token acceptance rate and low computation complexity. And then the last performance optimization I'm going to talk about is this aggregated serving. So this aggregated serving uses separate GPUs for prefill and decode. This allows to scale and control TTFT and TPOT independently. However, it adds GPU to GPU communication and adds more cost and infrastructure complexity. Depending on your workload, it can sometimes be worth it, but other times the cost outweighs the benefit. So use this technique with care. Now, switching gears, reliability. When it comes to mission-critical production application, nothing matters more than reliability. There are tons of scenarios to consider. GPU failures. GPUs do fail more often than you think. Network failures also happen more often than you expect. Microservice failures, database failures, cloud vendor failures. Even a cloud vendor may not be available. And sudden traffic changes, and etc. So how to tackle them? What are the principles? The first principle is redundancy. Critical components such as microservices and databases are deployed with built-in redundancy to eliminate single points of failure. Automated fast failover. When a failure occurs, traffic is automatically rerouted to healthy resources so users experience no downtime. Proactive monitoring and alerting. Continuous monitoring enables early detection of anomalies. And automated alerts trigger remediation workflows before small issues escalate into major outages. Graceful degradation. This one is also very interesting. In the event of a partial system failure, non-critical features can be temporarily disabled while core functionality remains available, allowing the service to continue under constrained conditions. Automated recovery, self-healing mechanisms quickly restore failed components without manual interruption. Resilience against large-scale outages. Even cloud vendors can fail. With geo-distributed multi-cloud infrastructure, inference services remain operational even in the face of large-scale outages. And we've actually experienced these kind of failures in the real world. And lastly, intelligent and reliable autoscaling. Rapid, reliable autoscaling handles sudden traffic spikes, ensuring stable and predictable services. That's a lot. So if you don't want to deal with all that, FriendliAI is for you. Friendly Inference is our purpose-built inference stack for speed, scale, cost-efficient, and reliability. At the inference engine level, it incorporates advanced optimization techniques, combining our own innovations with industry best practices and supports both language and multimodal models. At the infra level, we support all these features for reliability and performance. Intelligent routing for maximizing performance, auto-scaling for handling traffic variation, real-time enterprise-grade monitoring, tokens process, latency, etc., live model updates and model versioning, online quantization and speculative decoding. You don't need to worry about all these techniques. You can just check and then use. 99.99% availability with global infra for reliability and network proximity. And lastly, the integration with Hugging Face and weights and biases. With the integration, you can pull models from Friendly or push to deploy directly from Hugging Face or weights and biases. So why Friendly Inference? First, it's quick to market with extensive model support. It includes one-click deployment for over 440K Hugging Face models. And if a model isn't supported yet, we'll work with you to make it happen. Second, it's blazingly fast. For example, our platform supports over 500 tokens per second for Llama 3.18 billion on a Hopper GPU. Third, it's cost efficient, delivering more than 2 times the throughput of other solutions. So you can enjoy this benefit with the latest MOE models as well. And finally, it's reliable at scale, supporting trillions of tokens processed with 99.99% availability. So you can run AI models of your choice on our platform, friendly endpoints, or you can even deploy models directly from Hugging Face on our platform with a few clicks. 440K models are directly deployable from Hugging Face out of 2 million models. And we offer orders of magnitude greater coverage than any other alternative. Now, for companies with strict security or privacy requirements, we also offer Friendly Container, our high-performance on-prem AI inference solution. And if you're on AWS, it is also available as an EKS add-on. So just run a single command to install and integrate it into your existing EKS workflow. So at the beginning, I talked about the key goals. Now let me show you how FriendliAI delivers on them with a few customer testimonials. So first, LG. You probably know LG, well known for their electronics. So LG actually has their own foundation models called XL1, and they could launch their model up and running with all the optimization with enterprise-grade monitoring built in about a day. So quick time to market. And SKT is a large telecom enterprise, and they run their model with high reliability and low P99 tail latency. So that's another important thing. And AI startups, they gain significant advantages by running cost-efficient, large-scale operations with us. So several clients, they have moved away from closed-source models and successfully adopted fine-tuned open-source models on our platform. So Next-Day AI now scales to trillions of tokens using 50% fewer GPUs. Scatter Lab is another example. They credited us with accelerating their profitability break-even points by dramatically reducing GPU costs. Okay, so wrapping up, AI inference is critical. Latency, throughput, cost, and reliability time to market, or matter. FriendliAI offers a purpose-built platform engineered for speed, efficiency, scalability, and reliability. So you can focus on building great AI products while we handle the complexity of inference. One more thing, I have some news for you. So we recently launched the FriendliAI 10K AI inference credit program. So if you are scaling your AI and would like to try out our platform, you may be eligible for up to 10K in free inference credits. So scan the QR code to apply. It only takes 2 minutes. OK, thank you very much. I'll be around after the session. Feel free to come by and chat if you have any questions. I also have brochures on our 10K AI inference credit program if you'd like one. And I have 16 special soju cups, color-changing soju cups, if you like K-pop demon hunters. Thank you.